All righty. I think we have it going. Hey guys, what's going on? So yes, as we can tell from the title, that totally came and was suggested by the new YouTube suggestion feature. I'm like, oh, that's probably a pretty good thing. Do I have anything else to actually say? Well, I think I might actually have something else to say. Oh, hold on. Sorry. That's not for today. Not for today. You saw nothing. It's okay. It's okay. I know it usually takes a few minutes anyway for different folks to come in from different places on the internet, whether it's over on YouTube, whether it's over on the X Twitters, whether it's over where the skies are so blue, or some random Discord you happen to be in and be like, who is this crazy person that keeps on posting things again and again? But that's where we're at. And for all of our friends who may join us temporarily in the future, again, I understand. Listen, people got a lot of stuff going on. Good. There's a particular portion of the United States that right now is on fire. Terrifying. It looks like a Godzilla movie, but it's real life. So, hey, it's out to everybody out in California. But I see you there, WWKK. So, what we're going to be talking about today is going to be a vacuum energy explanation part two. All right. So, what we're going to do is we're actually going to do ROVAC because that's what it's actually called. I was calling it PVAC for like weeks and probably a couple of months and stuff. And Rick points out it's Rho, the lowercase p. It's Rho. So it's a little sideways kind of p. So we'll just do this. Okay, it's got a little tilt to it. Okay, so ROVAC. Okay, what's that? The vacuum energy density. Now, it is the vacuum energy density. That is the expression of ROVAC. Let me just double check. Go to our friend over here, ROVAC. Oh, of course it's gonna. Yes, I want all those vacuums. Oh God, vacuum technology is amazing. All I know is like 15 years ago, I bought top of the line vacuum. It was cost like $300 on something, like $250 on sale. Now you get like this little thing. Looks like the old Dyson things. Light as heck. Still got to plug it in. I didn't spend the extra $40 with a portable pack, but I'm like, oh my God. It's one thing that got cheaper, like $80, brand new. But wasn't quite as big or fancy. But I'm like, hey, I got so much carpet. All right, so let's do vacuum energy density because that's what we searched before. Let's share with our class. Oh, hi, Rick. Don't whatever you do, don't go back to the very beginning. It's we can talk about it later. Uh, vacuum energy density. Let's go to our other thing over here. Okay. So vacuum energy, blah blah blah. Let's get to something more manageable. We can actually read. All right. Okay, blah blah blah, all this stuff about 10 to the minus 9 joules or ergs, GVs. We're assuming the Planck pressure because that happens to come out. Yeah, we're off by like 120 orders of magnitude. Uh so may say it's a catastrophe. Okay. So what's the whole point? All right, I'm going through this. I spelled Rovac wrong, didn't I? Rovac. That. We're not. Ah, there we go. Yes, see, it is Rovac. It's the vacuum energy density. Okay, which is a running quantity according to our AI overview from our good friends at Google over there. The running vacuum is remarkable is characterized by a series of powers with a Hubble parameter as its time derivations. Okay, so we're calculating. It does compute. Okay. That's what I'm getting away. So what the heck am I talking about now? Okay. Let's go to it because we have the thingy here, and let's just go to the other thing. Let's go to our Wolfram friend. All right. So a lot of this happened because a while back, I mean, Rick has pointed this out. John Williamson, God rest his soul, and Thad have been like, you know what? When you look at things and In an inverse way, it might be a little interesting. Let's take our good old friend Big G, the Newton gravitational constant. Okay, we're on Wolfram Alpha, so we want the unit, not the letter or the note. So you see this thing here, 6.674 times 10 to the minus 11 newtons square meters per kilogram square. Oh, yeah, it's good math. There's no canceled out. God, units can be very confusing. What happens if we didn't want over this? Okay. One over the Newton gravitational constant. You're like, wait a second. It's a very interesting number. As Rick has pointed out, you can simply do something like this. 2 to the 7/12. Something 12 don't equal 10. Oh, that's interesting. What happens if we invert that? Oh, look. Looks to be the beginning of our big G number right there. Oh, very fascinating. Okay, that's not why we're here, though. But the whole concept of looking at things from an inverted perspective, taking a look at it from another side of the tracks, or perhaps another end of some geometric structure, while being inside it, outside. What's the inversion transformation? I'm not a geometer. Okay. But you start playing around, you start learning about like Planck mass, like mass. Ooh, boundary of mass that comes out from equations. What equation? This equation here, the square root of the speed of light times the elementary unit of action, Planck's reduced constant, divided by our friend there, big G. Okay, it's very neat. And then we could do unleash its energy, literally. We just multiply it by c squared. Ah, yes, we've done some magic. Okay. We have 1.9 gigajoules. I'm like, whoa. So we can computationally reduce that by just writing down energy because Wolfram Alpha has in its computational knowledge base. All right, cool. So as we see, we had our c squared term there times the Planck mass, that thingy there. All right, that's what we had. Okay, that's cool. I'm a child. I like to explore. I did one over it. Okay. One over the Planck energy. Ooh. Oh, what is this? Inverse energy. Oh, okay. And then you start to notice different numbers and powers. And then after playing around and looking at these different things, it's like 5 times 10 to the minus 10. The number looked kind of familiar. Why was it familiar? I don't know. Let's go to the cosmological constant problem because this is the Wikipedia article that actually highlights it in a way that I can actually kind of grok. Uh, okay, estimated values. Okay, 10 minus 27. Wait a second. 5 times 10 to the minus 10 joules per cubic meter. Wait a second. 5 times 10 to the negative 10. 5 times 10 to the negative 10. These are different units, and this is not the same number. We must note that, but I'm like, now the initial tagline for the stream is nature is simple. I learned that from Vanessa. It's like, okay, well, that's the same. What if we assumed nature was simple? How could we possibly get here? I don't know. Let's try to figure this out. Because number one, this is inverse energy. What is the Planck energy? Let's go back to what it was. 1.9 gigajoules. You can express an electron volt. Wait, joules. Wait a second. So that would mean that if it's in joules, what if we did our inversion thing with the unit itself? The numerology should be the same, right? All right, let's do 1 joule divided by the Planck energy. Oh, look, kind of close, but we don't have the right dimensions. What if, what if we did a little wizardry and if we squared our joule? Oh, look, We take an energy squared and we divide it by an energy. All right. Okay. But that's not quite there. We're not quite there yet. How do we get there? Well, let's say, what if we multiplied it by something? What's a good something? I don't know. How about our good friend pi? We'll put a protective bracket over here. Let's see what happens. Let's do the unit of curvature for circles and stuff. Well, we'll divide it. Okay. What do we get? All right, pi is joules. Oh, well, that didn't work anywhere near that I want. Oh, did it? Hold on. Let's do this. Okay. I need to make myself. Okay, so I get the same thing, but I get a 19. I don't know. Seems to be off. Why? Why is this not working? Perhaps we need to divide it by something. What might that something be? Or actually, do this. Well, we got 3 dimensions. There we go. I forgot my thought train process because I was off by an abnormally large amount of stuff. All right, wait a second. Okay. So what was that number we were looking for? 5.35 times 10 to the minus 10 joules per cubic meter. 5.354 times 10 to the minus 10 joules. All right, we're still off. We get that 3.34 giga electron volts. It's 3.35 giga electron. Wait a second, we're missing cubic meters. Well, because we can. Let's just set our parameters. Let's divide it by meters cubed. Is that what we're saying as a parameterization? We're expressing it in cubic meters. All right, that's based upon the measurement that we got from the Planck satellite and stuff. That seems to be our best estimates at this time and stuff. Oh, look. Wait a second. 5.35. That appears to be approximately the universe vacuum energy density. What do we got? We got 5.354 times 10 to the minus 10 joules per cubic meter. 5.35, and then we deviate. So instead of 4, we get a 6.6. So we have about 3 significant digits of accuracy. And I did the whole thing where I literally set it to c squared on the other side, which is absolutely a fascinating thing. If you actually start to go through and start to look at it, you're like, wait a second, why could I set this equal to 1 of c squared? Because that's a very interesting thing. I just thought this kind of, I don't know, maybe it gave me the Richard Feynman vibe because it kind of looked like a set of drums or something or bongos. It's like, wait a second. What you're saying is, in order to calculate the vacuum energy density, the conjecture, the way to do it is you do pi joules squared, or unit of energy squared, times our good old friend pi. We divide that by, well, we got like 3 dimensions of space. So that's probably going to be doing some energy density for our cubic volume, and then you divide it by the dimension cubed, the dimension of volume. And it happens to come out to be something very pretty like this. I can intuit a little bit more because before I was doing, because you could also rewrite it as just bring out the pi, you bring out the 3, bring out your pi, bring out your 3. Just multiply by pi, divide by 3. You get the same thing there. Um, I mean, again, you can rewrite this in other ways. This is just the easiest way for me, just because I'm like, well, I got a pi j squared divided by 3 EP divide by M3. It still isn't as pretty as an E equals MC squared. Oh, what am I talking? Again, this just happened to be something that happened to hit. It's just a bunch of numerology. And again, I'm going to stand by numerology is numerology until it explains more with less. Okay. Let me get back to what we were talking about. I wrote like one dang thing on the board. We're already like 15 minutes in. Hey, K Shaw. Yes, yes. And we got some violence here. It's hey, listen, man. This is how you cover your butt. You conjecture. Why? Because I think a lot of folks go out there and be like, it is obviously the case. So you go from saying that we're entertaining an idea here to this is fact. The problem is if you're going to say this is fact, you're going to run back a little bit more. Yeah, okay, there we go. Well, not all of the top of my head is always cut off. Okay, let me raise that. But the thing is, if you're going to state something as fact, number one, most things are wrong. If most things are wrong and you're going to go out there and be like, well, this is right, it's like, all right, hopefully you have a very strong foundation for what it's built upon rather than I said so. Maybe that's the case. Now, what happens to be a deity, maybe that is the case. I'm just a meat bag out here. Okay. Uh what the heck did we just even conjecture here? All right. We conjectured that the rho vac, or basically the vacuum energy density of space as we know it, we're going to claim that's equal to pi, because who doesn't like pi, joules squared, big J, O-U-L-E-S, and the power of 2. We divide it. And again, this is my best interpretation right now. I do a calculation, it gets some numbers, it has a certain level of accuracy. And again, you're going to have errors and stuff like that. And we're going to need better equipment to see if there's any there, because it's very significant pitch. It's insane. To be fair, I think most of the time of our knowledge of the speed of light, so to speak, we had 0 significant digits. We thought it was like a we thought it was like a 3. It seemed to be like a 3. It was 3 for like 3 significant digits, and then oh, 0.9979. Heck, I still even will throw in that 8 there after the 2 nines. Why? It's an approximation. It makes things easier. Things can stray after 3 or so significant digits. It's probably something to be aware of. All right. So we got pi. So curve of something times energy squared. Energy squared. Oh, that sounds like some OG, some some equations from about 100 something years ago. It's 120 years ago. Wow. All right, that's 5 factorial. Cool. All right. So we got our curvy thing, our energy squared, a unit of 1 within a system, because it's literally the mass equivalent of like c squared for a joule, which is interesting. And then we get this squared. All right. We got 3 dimensions of space. All right. Well, maybe we should divide this by 3. It also makes the answer work. Then we put our friend in here. Planck energy. Why? I'll use the Planck force to conjecture a potential size of small u universe, so to speak. I keep saying that because it's, oh God, I can't write a K. Wow. Like it's doing like a flip kick. Or listen, I'm not trying to do the Chuck Norris roundhouse kick here with our Ks, even though that would be kind of cool. So the Planck energy. There we go. All right. All right. So this will give you the energy, but the thing is, it's actually energy density. So this is the probably drill more holes. Hold the board. Energy density. You find energy density by cubes. So it's like, all right, we'll bracket this up just because occasionally, depending on how you put it together, you might get a slightly different answer. Protected it. Let me just divide it by meters cubed. All right. Because we're setting it to the volume of a cubic meter. So is it really that unfair a thing to be like, well, let's divide it by a cubic meter? All right. So what do we have? We have pi, circular curvy thingy, times joules squared, energy squared thingy. That's divided by 3, the number of dimensions of space we're working with, times a base energy, the Planck energy. And then we just divide that by our standard meter cube metric. Okay. And that happens to give us at least the first 3 significant, at least, let's say this, 3 significant digits. Okay. To be fair, it's about 2.5. You can't really have 2.5 significant digits. It's got 2 significant digits for, I think, the mass, because you can just redo this. Go back. Hey, we got vibe. Hey, listen. Hey, a whole bunch of meat bags. We got a little bit of a fraction of an instant of time here. I think we can do some really great things, because I've been on the internet long enough, and I think we're gonna see some really interesting stuff coming out there. Quick side note: anybody's taking a look at some of the things that come out of the Consumer Electronics Show, like CES or whatever it is? Oh my God, what's that? Like the Nvidia CEO goes out there, and like one of his first things is, here's the actual chip from one of like our supercomputing sites. It's got 1.4 exaflops of things, and it's literally a thin wafer. This set, it's like, yes, you can stack all these things into it. I'm like, okay, this is why Nvidia is making like, yeah, a ridiculous amounts of things. And then he comes out with like something the size of like a Mac Mini in his hand, and he's like, yes, this runs all our AI software. And stuff. What? What? I'm like, this dude is a wizard. Probably start covering some tech stuff and everything too, just because it's fantastical. And this is where the engineering comes in, because once you start getting the engineering going in, it's pretty awesome. Oh, I see Rick has a request for an endorsement for I think the archive. Cool. Good luck with that, my friend. Uh, here's the thing, man. I'm sorry, I'm assuming man there. We'll just call you V, because V is cool. Uh, I just look for simple. I'm a simple dude. If anything, I'm a gamer more than anything else. I just look at stuff, and a lot of the stuff I do, it's usually because I don't know any better. Because if within science, like folks are like I listen to the Dr. Hossenfelder and Dr. Matt O'Dowd and stuff like that. Like a lot of folks out there, if you're interested in some science, some physics, what is going on in our universal stuff and things? I heard from plenty of them. It's like, you cannot calculate the mass of a Higgs boson. I mean, to be fair, I may have heard that and then just didn't pay attention to it. It's because why? Well, you're not supposed to. Oh, it's we have to do that by measurement. There's no way to do that, or the fine structure constant. So it's like, okay, well, I don't know. I just if we had certain assumptions about different things, and again, oh, I'm sorry. Let me share with the class. All right, I'm going to this. It's just when you start looking at things, and this is the thing. I'm no genius or something. I'm just a very blessed individual that happens to be. I was decently good at some analogies and stuff like that in school and stuff. Never was really like a super smart kid or anything like that. But it's like I have interest in things. I'm a gamer, so I'm willing to try some pretty crazy things. And now that we have modern computers, I can literally just do something like this. Oh, it's let's just say the Higgs mass. Let's just divide it by another mass. The Planck mass. 'Cause we got our 5 Planck constants, so we can use the dimensions to reconstruct quantum field theory. Why not? Like mass. And you do this, and you get this number here. And you're like 10 to the minus 17. I think it was. Oh God, I'm still gonna get her name wrong. It's the doctor that Professor Sean Carroll had on. Hold on, let me go to my YouTube channel. Wait, find it. Let's see. What we got? AMU was, I think, oh, this guy. Hold on, I was, God, like mixing angle. Oh, no, 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 no. That's the next one. All right. This one. Yes. Right here. All right, Dr. Carrie Cesarati. All right, I apologize. All right. So why am I saying that? Okay. Did you get this number here? If you just divide the mass of the Higgs, and actually we'll let them. Let's actually watch it. Let's share the actual tab. Okay. Go. All right. So here's the claim of this guy. All right.
Well, maybe the Higgs needs to be what the Higgs is because it helps set the magnitude for the elementary unit of action. Let's take two. Hopefully.
All right. So we'll let her explain.
Hierarchy problem. It's at least according to Sean Carroll and oh my god,
And yes,
I'll put her name up here. They had a discussion.
You mentioned the hierarchy problem. What is this? That sounds like politics, not physics.
I mean, these days, kind of hard to disentangle, honestly. Yeah, so the hierarchy problem is something specific to understanding the mass of the Higgs boson, which is one of the bosons in the Standard Model. And the Higgs is the weirdest particle in the Standard Model by far. It is the only particle that has the properties that it has. So, like I said earlier, a lot of particles sit in 3 generations. The Higgs boson does not. The Higgs boson stands as a very weird outsider that you may have heard is responsible for giving particles mass. And if you want to learn all about that, there's a beautiful book by Matt Strassler that you should definitely check out.
Very good.
But the Higgs boson gives particles mass, has different, what we'll call, intrinsic properties. It's called the spin in specific that doesn't match any other particle. And because of that...
Do not have excessive fine tunings. Okay. I'm just pointing out, at least this is what Wikipedia says. I don't know, maybe people disagree with it. Let's let the good doctor continue.
We think that the Higgs boson should have a mass 10 to the 18 times bigger than it does. And so this is the hierarchy problem, and the hierarchy is just the mass scale that we expect and the mass scale that we see everything else sitting at. And the fact that there's 10 to the 18 differences, I mean, really 10 to the 32 because it's squared, and that's the real first principles number. The fact that something could be off by 32 orders of magnitude from our theoretical predictions, where did that come from, right?
Listen, there's a lot of numbers, so it's I assume that's what she meant there. Again, maybe I'm just completely missing something. Maybe it's divided by 4 pi or. So the thing is, you see that you're like, okay, let's go back to our window over here. Okay. Boom, and okay, so we have that, and then we said it was squared. Let's look at the squared value. Okay. And listen, back in the day, you'd have to go through like all these journals, have all these things, have all the numbers, have your calculators there if you had a calculator, and do these computations. Right? I remember doing calculations with a TI-83 or something like that. So it's like, I remember those days. Now we have Wolfram Alpha, so it does the calculations for you, and you can literally just type in words. And it will give you at least to a certain approximation, and then if you want to verify, then you go to CoData or like HBAR or something like that. You would go here, you would find the actual numbers here to more significant digits is what's currently defined at. But for at least the first level approximation, just to see if maybe there's something interesting worth more investigating, that's why I personally like using Wolfram Alpha. Okay. So I blathered over and fanboyed over Wolfram Alpha and CoData. Okay, so what else are we talking about now? Let's take a look at our friend here. So what do? We took the mass of the Higgs, divided by the Planck mass, and we square it. What does that mean? You get this number here. That's a really tiny number. If you're in physics, that shouldn't mean a dang thing to you. It's 1.05 times 10 to the minus 34. I've been going down through enough Wolfram holes. Eventually, you start to pay attention to certain friends. And again, I ain't no genius or anything, but I have, I think, a semi-videographic memory, and I'm pretty good at remembering the first three numbers and different constants and like their exponential powers, or at least pretty close. Because every once in a while, like, wait a second, that number looked familiar. 0.05 times 10 to the minus 34. Well, how about h bar, the elementary unit of action? 1.05 times 10 to the minus 34 joule seconds. And we see there's an extra 5 there, but if we go down more digits, we find out that's actually a 4, and the next digit a 5 and 7, so they round up there. These are things to keep track of. But you see this, and you're like, all right. So at least the first 3 digits, again, we don't have a dimension there, seem to correspond with this. What the good doctor said was an important thing. It's not just a relationship, it's a relationship squared. So hypothetically, now we're putting in the Higgs mass right now from the Higgs mass thingy. Okay. What is the Higgs mass thingy according to Wolfram alpha? About 125 giga electron volts. Hold on. Divided by c squared to get out. Actually, they're rounding there. Oh no, times c squared. Sorry, to get its energy. Oh, did you just take off the last 2 significant digits? If I do I have to do particle to have it list more data? Interesting. Okay, there we go. Yeah, so it's based on 125.18. Currently, it's between about 100 and go back. Higgs boson, I know, on the other side, John. Higgs boson mass. May have Googled that a few times. All right. According to Atlas, 125.11 plus or minus 0.11 GeV by c squared. Okay. CMS, 125.35 plus or minus 15 GeV divided by c squared. All right. And that was in 2022. Well, those are the most current measurements we have. Okay. So hypothetically, let's say we were going to try to solve for it. We're going to try to do something crazy. What if we assumed it was equal to the magnitude of h bar? I mean, that's a crazy idea. Is it crazy enough? So basically, we're getting a dimensionless thing here. Why? Because we got a mass term divided by another mass term. So we need to keep a mass term in there. So how about we solve for x kilograms? Okay. Let's set it equal to something. How about I don't know. Set it equal to, oh, what did we use earlier? We used our friend Joule squared. Do we need Joule squared? Or would we be okay with just Joule? Because we need to cancel out our dimensions, remember? So Joule divided by h bar. What would we get? Hmm? Uh, uh, that helped. Oh, wait, I'm a dummy. Because it's Joule seconds. I'm in the wrong dimension, bro. Okay, 1 Joule second divided by h bar. There we go. Stuff. We got our graph. We actually have 2 answers. We have a negative answer. We have a positive answer. Oh, what did I do here? Oh, I did something totally wrong. Cool. Joule second divided by h bar. Oh, is this squared too? Wow, I totally broke it. Oh, do I usually express it the other way? Oh, do I just need to do h bar over joule? H bar over joule second. All right. There's only so many possible mistakes I could make. Countably infinite, perhaps. Okay, at least we got the right answer now. Not like back in the day where I would try to do a video and just like copy Thad with what he did and just be like, I made an error. And it takes me like 40 minutes to figure out I used the Planck time instead of temperature. Why am I off by 76 orders of magnitude? That's usually why. I digress. Like they're abstract though. Free the 0 point energy. There is another video on that. To be fair, according to Stephen Wolfram, mining energy from the vacuum using matter or things following the laws of matter. He doubts you could do that. However, he suspects there's a potential field configuration. I may or may not have cited that 1981 paper with Jim Amjorn in a poster I presented last year. Because I had almost never heard it anywhere else. Higgs bosons are strange. That is true. Upcycle. Precision goes up by 22 over 7. Oh. I mean, that isn't. Wait a second. Is this true? Let's check. 22 divided by pi approximation, because that's always an interesting thing. Give us a little offset. Oh, that does seem to improve it. Hold on. 5.356. Where are we at? Values 5.356. See, that's very interesting. That's very. See, the problem is we only if you look at the mass term here, we're basically getting these other terms by basically taking that mass and then like multiplying it by like c squared y, because this is about 16 orders of magnitude or so between c squared, 16, 17 orders of magnitude between these two things. We only really got a 2.5-ish right now with that. But that is very interesting. And even 22 over 7 in and of itself. I mean, 22 is half of 44. And 7 times 2 is 14, which happens to be the number of digits that have been at least verified by experiment within the standard model, as well as the digits of precision of Einstein's general relativity. Wow, that is some loud wind. I'm sure it's muffled, but dude, I got like a window over here, and I'm like, I can hear that. It literally blew like the roof off a door, and like it's the front of the car, and you're like, that actually hit it pretty good. I'm like, that it was a good enough thunk where it's like, I'm not gonna deploy the airbags, is it? Because that would be a really bad day. Kind of need those things for in case there is a deadly accidents rather than just a. But dude, the poor folks in California, I'm watching like Polly and stuff, and it's like like a tree literally just like blow right down. Maybe it was Cameron or something like that. Literally just like had the tree just blown right down next to them, just misses the window and stuff. It's like 100-year-old like palm tree or something. It's like those are pretty good sized trees. But Dr. Abstracto is comment. Oh, for row. Oh, all right. Let's see what happens. What do we got here? H bar, joule second. I don't think I have pi in here. Let's see. Oh, okay. No, I'm reading. Okay, yeah. Okay, I'm ready. I assumed that just because there wasn't a pi in this other calculation. Okay, so when we actually put this in, what the heck did we do? All right. Here's the crazy thing. And again, let's get some videos of this, but again, a little bit better with at least playing around, and I'm sure somebody out there is going to be like, "Look at this," and it's like, "Oh, that was even a lot easier. Thank you." What we're doing is we're noticing if you take at least let's take this. So we're noticing that if you take the Higgs mass, the thing we're not supposed to be able to calculate, and we divide it by the Planck mass, and we take its squared relationship, we throw the protective brackets on, so they're both getting squared. They're both a dimension in kilograms. It cancels out. We get a dimensionless number here. Okay, we notice that. All right, cool. We notice when we do this, what do? We took h bar, elementary unit of action. We divide it by the literal units of action, joule second, or in this case, 1 joule second. We notice we get out at least the first 3 digits of that. All right. We conjecture that this mass over here, if we set this equal to this, we should be able to solve 4 dimensions of kilograms, kg there, and we solve for x. So this is going to give us a dimensionless number. This within these dimensions will give us a dimensionless number. And we just solve for x. It gives us this thing here. And again, we do get a positive and a negative number here. We get our parabola effect. And then we get this value right here. And again, there's a negative value. I don't know what that means. Perhaps we could invoke the positive mass conjecture, positive energy conjecture, something like that. Again, I don't, that's just what comes out with the math. Like I put absolute brackets or something over there. It makes you better, to be fair. You could actually just express this as like mass of the Higgs over the Planck mass squared set equal to the absolute magnitude of h bar. That's the prettiest way to do it. It usually doesn't work unless they update it. Let's see. Because we'll get the dimensions out by itself, but as soon as you run a computation, it isn't really a fan. So let's see. Does that do? Okay, so it's just giving you the same thing there, because if you just do that, it's going to take Planck constant, blah blah blah. Okay, it's still giving us. We'll do it if I do the absolute magnitude. Absolute magnitude. Yeah. I think it only really likes to do it when it's like that. I do. Absolute magnitude, it's doing something else, throwing about. Okay, so magnitude and base AI. SI, pardon. Let's try that. Will that work? Nah, it still wants you to do it. That's all right. No, I mean, that's just a little claim. That's why it's, yeah. When you see something like that, I'm like, maybe there is something to that. We have a unit there. It's a simple thing. It's implying there's literally curvature, there's squariness, there's 3 things, and it's within a cubic dimension of volume. What do you want from me? It's okay. No, we'll write papers about all this stuff, and I do the more paper stuff than actually trying to catch up and everything. Oh, Rick is up. Hey, God bless, man. Hopefully, it's all right up in your neck of the woods. Hopefully, I think Washington's gotten some more rain, but it's crazy. It's like 100-mile-per-hour gusts and stuff. It's like it's not a hurricane. It's like a wind crane. It's no, and that's the thing. And then you look at like the middle of the country. The middle of the country is just getting wrecked by freezing temperatures. The wind is pretty nutty up here, and even over in like the United Kingdom and stuff like that's freezing. You've got from 10 Downing Street, you've got Larry the cat warning people and felines to stay inside. Oh, the heck of a time to be alive, folks. But we could my thing is I think we're gonna have to wait till we get to more missions, because even if I'm gonna conjecture that, it's you're going to really need to have a measurement, probably about 7 significant digits, because then if you have some inaccuracy in the last two, you can have at least have a solid 5. That gives you statistically much stronger confidence, and I would say at least evidence, because it could still be wrong. There's still probably going to be some deviation, and even within what is it? If we take Thad's energy conversion thingy manager, here. So I think the Higgs boson, yeah, this ends up being its mass. That's the calculated value of h bar. And when we apply the energy conversion, I think it's this. That's like that. Yeah, so ultimately, if we had the precision and there was something to this, the full calculated mass energy should be 125.3756405907. I think that might be a 6 at the end, but it's just rounding up. Giga electron volts. And again, that's gonna need to publish a lot of things. They're gonna need some more measurements and stuff like that. Because right now, for the Higgs boson, it's what do we got? Looks to be about 125 giga electron volts. That's even what Wolfram Alpha was telling us this. And then it looks to be a little bit more with some error in the last 2 digits. Okay. More accuracy is needed. Looking for group muon collider. That's mostly what we're looking at. Oh, that's actually good. All right, we could probably use a little balmy weather up here, so feel free to visit. But okay. So let's go back to our friend over here. Been going on for. Let's actually take this out. So we got this thingy, and say the problem is that 22/7. You could say that, but now I would need to be able to explain why that 22/7. There's a lot of fascinating things over that. It's a lot easier to invoke pi and walk away. And again, this is just my best. If there were something to this, because you can. Oh, let's actually just go back for a second, just because we have this thing in here, and we got joules. So, what actually happens if we did change this? Because before I could just do Planck mass. Oh wow! Rainfall runoff erosivity factor. Don't know what that is. So we would need something instead of energy. Oh, just the kilogram. Is that really what it is? Kilograms? Is it really just kg? No, it doesn't work quite the same. Oh, this is interesting. Oh, this is going in a different way. Mass density. Because before I was just setting it equal just to a joule. Oh, I probably need to. Oh, here. We need to divide by c squared. There we go. There we go. All right. Why does that still get us the vacuum mass? Like, oh, okay, we're getting the same units. Okay. Just because this joules is already expressed in energy, if we divide it by C, we're getting the energy out and we're just getting a mass term. So then we could do basically the relativistic mass of joules squared divided by 3 Planck masses divided by a cubic meter there. And then, yeah, we get the same thing in energy density. I mean, that's neat and that makes sense. But, yeah, this is the thing. We have the internet. And that's the beautiful thing. I'll come across somebody, it's like, oh, some professor that put a lecture up here. It has 3 views on the video. and the algorithm is pretty good at showing you what you see. If anything, that's the thing that I'm like leveraging. That's how I found most of the interesting things. Is usually like I'm going through, I'm listening to things, I look into things, and all of a sudden something gets recommended. It's like, oh, that seems kind of boring. You start listening to it, and you're like, oh my god, I've never heard it expressed in that way before. And all of a sudden something just clicks. And dude, this is where even some of the papers where I think Dr. Hasselfeld was making fun of some paper just because what is it? Oh god, the what is it, like new engine and some engineering blog or something caught up with something like, oh, here's a new theory of everything. And you go through, and when you just kind of read it, it's like, well, they said they were using like a Planck time and length as building blocks, and it makes sense. And I'm like, I'm actually kind of interested in that. You start going through and like there's things that are just empty boxes, and apparently within the physics community of Thailand, they're suing people, and people are like outraged and losing their minds. And Dr. Hopsville is like, I have no idea if this is a troll paper or some people were just kind of trying because they said some interesting things, and then I went through the paper and like I did a couple of calculations. I'm like, these are just wrong. Like it's not even just like a little off rounding ever. It's like, no, you're not even the right dimensions here and stuff. But then at some point in there, I just looked at an interesting relationship and I'm like, well, what did I put the actual numbers that probably should be in there or the constants or anything? And it was actually really cool. And it's unfortunate. That's why I think one of the easier things to do is like if you got something to say, if you can simplify as much as possible. And that's the big thing here is because now we have tools that your average Sally, Dick, and Jane, if you can do some basic reading, maybe a little bit of like the 3 R's, reading and writing and arithmetic, it's like, wait a second. 3 of those things do not start with R. Not even 2. But I mean the meme persists and people would say that people understood what they meant. Like took them seriously, not literally, and that's one of the things. Hey, Titan, good to see you, my friend. Good to see you. Well, that's the thing. If anything, I ain't the strongest, fastest, smartest dude. I may be the luckiest son of a gun in the world. The reason I say that is just because the amount of connections you randomly. I'm gonna go for a run on Twitter. I got tired of burnt out of politics. Let me learn. Let me email Dr. Rick Weinstein because apparently, if you wanted to work on geometric unity, you needed to get his permission. So I sent him an email. I never heard back. Coincidentally, that same week, I'm out for a run. Open up Twitter. Trolling Professor Wolfram and Professor Keating a little bit just because it's like, it's this different research. I have no idea if this is related. If people discover interesting things, maybe they should catch up, be more aware. It's a little lighthearted trolling. Then Nolan starts to troll me. He's like, I had some hip hop music and Thad Roberts. I mouse over and it's like, oh, Thad Roberts, theoretical physicist. Oh, I like that stuff. All right, click follow. All right. Long story short is that same week where Doctor was it? No, I think it was in the week or the week after. Was it Doctor Weinstein goes on and he talks about geometric unity and all that stuff. It's like, whoa, this is pretty cool. I sent an email and stuff, and then that week, all of a sudden, I'm just out for a run. All of a sudden, Twitter is. Wait a second. There's a post of that physicist guy. It's happening. Let me click on this. I'm listening. I'm just going out for a run, and it's like platonic solids, a whole bunch of bold claims. I'm like, well, if half the stuff this dude is talking about is true, this would be revolutionary. I take it with a grain of salt 'cause it's a dude on the internet. I'm a dude on the internet. All right. Then by happenstance, the very next day, they released the mu1G2 results. I don't know what a mu1G2 is. I still don't really know what a mu1G2 is. Some gyromagnetic moment. Okay, it's wobbling. It needs to have a correction at some point there. Very precise measurements. Seems to deviate from the standard model at the time until we QCD'd the heck out of it. Or lattice QCD'd the heck out of it. All right. But apparently at the time, it's like, This is our Mars rover moment. People are like so excited, like this is a big deal. I'm like, all right, I'm listening. They talk about the numbers, no idea what it means. And then I'm like, all right, I'm at work. I'm like, well, release this. I was listening to this while I was working. I'm like, I tweeted the dude just because I'd listened to his thing the night before. I'm like, I don't know if you covered this all. Do these results help your model? He responds, yes. I'm like, all right, that's neat. I attempt to do journalism, my friends. What do? Go home after work, go to Fermilab's website, look at the numbers, not knowing what they mean, just look at the numbers. Go back to the video that had premiered the night before while I was going out on a run, and all of a sudden it's like, dude, man predicted the mu1G2 results. What's going on here? Some more research, interviewed him a couple of times, yada yada, this, that. Very blessed in life. Somehow I become a physics monk. But yes, it's good to see y'all. It's good to see you all. We're just kind of like attempting to wrap up here, even though I didn't really write much on the board. All right. So the whole claim is, all right, the vacuum energy density. We have no idea. We have no idea why this. It looks like a PVAC, but it's the Greek symbol. I think it's Greek. Rho. It's rho because it's the little weird lowercase p vac. All right. So it's an energy density term. So what are we saying? The whole thing is if you want to get that number there, at least for about 3 significant digits around our level of precision, first level approximation, it appears to be this. What's that? 5 joules squared divided by 3 Planck energy divided by meters cubed. Is that significant? I don't know. I guess we're going to have to see whatever actually happens. We're going to need more precision, and maybe that's totally off, but I don't know. We're just breaking things up into units. The unit of energy. That's a unit of energy. This is a volumetric thing. I get some high energy stuff divided by a 3 energy thing divided by a volumetric term. We're gonna have to, and this is one of those things where I'm very quickly realizing that I really just need to finish the papers, get them out there, see if we can get some refereeing, some improvements or something, and see if I can actually get them published. Because realistically, a lot of stuff is probably going to take at least 10 or 20 years to actually get to the precision to be like, all right, there's actually something significant here, or, oh, that was just a little fun numerology. So, because I'm going to stand by it. That numerology is numerology until you explain more with less. Because that just seems to be how it works. Did we have any other interesting calculation? Oh, yeah. Oh, I didn't even show the thingy for the Higgs. I apologize. What's going on? A random other jaunt there. All right. So here's this. Here's expression again. So that little thingy for the. Oh, God. Wow. I'm really just this bad at this. Move forward. No. Oh. H bar joule second. Okay, that's good. So, all right, we got this positive and negative thingy for the Higgs. The sense up here, we're solving for kilograms or x kilograms. We're solving for, it's easier to see here. X kilograms divided by the Planck mass, the whole thing squared. Is the elementary unit of action divided by the unit of action, essentially a 1, so to speak. We get this number here. If we go over here, we'd solve for kilograms. We just toss our unit back in, we get kilograms. We get approximately the mass of the Higgs boson, but we usually see it expressed in GeV. Let's look at it expressed in GeV. So kilograms by c squared, release the energy, bro. 25.37 GeV. And 25.11, error of 11 in the last two. And 25.35, error of 15 in the last two. So it's about I think it's about 2.3, 2.5 sigma from the Atlas thingy. It's about 0.2 sigma from the current CMS measurements. I mean, wouldn't that just be it all? Why does the Higgs mass have the Higgs mass? Well, is it in order for the elementary unit of action to act? I don't know. It's a fun thing to think about. And listen, hey, we're conjecturing here. You learn little things. Hey, listen, this is the thing. The good thing is, too, as long as it's small, I can actually spend a little time. If we get more folks here, I literally, listen, I have enough trouble dealing with like 10 people watching. So as 100, I'm totally screwed. But oh, this was a nice little thing we had. I spent a good deal of mental energy on some other things earlier because we'll see what happens. We'll see what happens. Certain things need to have some back channel discussions, and we'll see where we go. But other than that, hey, thank you all for watching. Take care of yourselves, everyone. It's a crazy world out there, but it's open to a better tomorrow for y'all.